Bond enthalpy, the strength in between a chemical bond. You'll catch up on your vocabulary code using the QR code here. All right. Okay. And so bond enthalpy is defined as the energy requires to break apart uh, two different atoms so that are bonded together. So we're going to break them apart. That's the general idea. So essentially, enthalpy can be calculated a couple of different ways. One of them is by experiment using the calorimetry. You can also do it by looking at a chemical reaction, and just by taking the energy of those chemical bonds, you can predict what the enthalpy change should be. So this is a very theoretical, on paper type calculation. All right, a couple of things we got to remember is that breaking bonds, the delta H will be positive, which means it's endothermic. So positive delta H means endothermic. It take energy goes in. Forming bonds, that's where delta H is negative, so it is exothermic, and so energy goes out. Out. I'm going to draw a better arrow. So to calculate the enthalpy change from bond enthalpies, what you'll do is simply take the bonds broken minus the bonds formed. I've got a cute way to remember this in a second. So it's the amount of energy needed to break apart 1 mole of a bond to give separate atoms, and it has to be in the gas state, and the units are going to be kilojoules per mole. And then bond enthalpies are always positive, like they're reported right here, positive 242. And that's because they're always thought of as endothermic. It takes energy to cut this bond in half. So it's going to require energy to break that bond. So that's always going to be a positive number. It's going to be endothermic. Hopefully you get that idea. So you're not expected to memorize all the bond enthalpies in any given question. You would be provided with them either in a table or specifically the ones that you need. But here are the ones that are the most common for single bonds. So the hydrogen-hydrogen bond is 436, and then carbon to carbon is slightly weaker at a 348. Okay, so the higher the number, the stronger the bond. So the nitrogen-nitrogen bond is very, very strong, which is why it's so unreactive. Hopefully that makes sense. All right, so to calculate the delta H for the hydrogenation of ethene, what you would be provided in a pre-AP chemistry class is you'd be provided with the Lewis structures here as a gas, and you'd be provided with this Lewis structure of the reactants. Okay, so this is ethene, and this is hydrogen. We are going to hydrogenate it by adding hydrogen to it. And so we're going to break that double bond right here. We're going to turn it into a single bond, and we're going to stick hydrogens on it. That's called hydrogenation. All right. So the energy absorbed to break the bonds can be calculated by taking the carbon-to-carbon bond, which we know is 612 up here in our data table, and there's only one of them, right? So there's only one of them. Now there are 4 carbon to hydrogen bonds. Now look at there. That's 1, 2, 3, 4, right? So we're going to take the carbon hydrogen number, which is 412, right here, and we're going to multiply by 4. So make sure you multiply by those coefficients. The most important thing is that you be careful and you count all the bonds in all the different sides of reactants. I am looking only at the left side of the reactants at the moment. That's all I'm looking at. Okay? Because this is the energy to break bonds. This is the break side, the breaky side. And so what we'll do is we'll add them all together, right? And we'll get 2,696 kilojoules. Excellent. All right, now we're going to do the same thing to the other side. This is the makey side. So we are going to form bonds here, right? So we're making bonds. And we've got the carbon-to-carbon single bond. Now notice this one's new, right? This didn't appear in our reactants. So we've got to go find a new number, that's 348. And then this carbon to hydrogen bond is again showing up as 412. Now, notice that there are 6 of them now. 1, 2, 3, 4, 5, 6. So you will have to count them, all right? Make sure you count accurately because your answer depends on it. So whenever we add those numbers together, add 348 plus 6 times 412, we will get 2,820. Now notice that 2,820 is larger than 2,696. So that means that the bonds of the products are stronger. Now, if their bonds of the products are stronger, that automatically makes it exothermic. Okay? And I'll show you why in a second. So what we are going to do is, since these bonds are formed, this is always exothermic. This right side is exothermic. This number is negative. This number is negative. Because we are forming bonds. This is negative. We are breaking bonds here. So this is positive, and this is positive, and this is positive, which makes this side positive. It will always be like that. It will always have the positive on the left side and the negative on the right side. Now, essentially, you have a positive number and you have a negative number, right? And you will simply add those two numbers together and you will get a final answer, and then that's the answer. Okay? No big deal. You just got to add them up. What students miss is they miss a bond, they count incorrectly, which, it happens. And then they forget to multiply by their coefficients. That tends to happen a lot too. Okay, so try them one more time. We've got, again, a full chemical reaction with the Lewis structures. We've got the nitrogen to nitrogen bond. We've got a nitrogen to hydrogen bond. There are 4 of those here. And we got the oxygen-oxygen double bond. So what we're going to do is we're going to calculate all those together. And again, we're going to split the sides. We're only going to look at the reactants first. So the nitrogen to nitrogen, nitrogen to hydrogen, and then the oxygen double bonded to oxygen. Perfect. We'll add those all together. Remember, these are all positive numbers. Good. All positive. Making this number positive. Okay? Positive 2,211. On the right side, we are now forming these bonds. This is the makey side. And so be careful. This has a coefficient of 2 in front. Sometimes you'll draw 2 different water molecules, right? This means that you have water twice. So notice how there's an oxygen to hydrogen bond and an oxygen to hydrogen bond. But since there are 2 molecules, there are actually 4 oxygen to hydrogen bonds. Everyone should notice that and pay attention. This is where a lot of students miss stuff, is they're not paying attention to the coefficients. All right? So coefficients work just like math. They need to multiply everything that's in that term. Okie doke. Now there's only one nitrogen-nitrogen triple bond, so we'll put that number in there. 944 plus 4 times 463. Add it together, we'll make 2,796. We compare the two numbers. The products seem to have a higher number, which makes this exothermic. Okay, if the reactants had a higher number, then it would be an endothermic reaction. All right, so this would be a negative number right there, because this is negative and this is negative because we're forming bonds. So we take the positive number from the reactants and the negative number from the products, and we just combine the two together by simply adding them, the positive and then the negative, and then we get a negative 585. So this is approximately how much energy would be released for this chemical reaction. You can use any chemical reaction you want, do it by this method, and you should be able to predict how much energy is released. Now there are some limitations because this is on paper, this is theoretical, this is not the actual thing. One limitation is that this has to work for a gas, so it does not work for liquids or solids, okay? So that has to do with all the intermolecular forces of a liquid or a solid. Remember, gases have no intermolecular forces, so that's why we can assume this. And then the average bond enthalpies are different for each different compound. So these numbers are an average. What I mean by that is if we have an oxygen in water, oxygen hydrogen bond in water, this is different than an oxygen to hydrogen bond that would be if this oxygen was tied to a carbon atom. Okay? Just because of the electron structure of the neighboring atoms around it, it's going to affect how strong that bond is because of the electron pull and the electronegativity and all that stuff. So this OH bond is different than this OH bond. But averaged together, you get the number that's on the table. So, all right. So they're not necessarily hyper accurate, but they do give you a pretty good idea. Other than that, that's pretty much it. And have a good day.